In this section, we're going to take a look at the sum and difference identities, also sometimes called the sum and difference formulas.
All right, so let's start off with a couple of angles. And to give ourselves a coordinate system, we're going to go ahead and put those angles in standard position, meaning their initial ray is along the positive half of the x-axis, as always. Now we're going to take these two angles, and even though they have the same initial ray, we're going to have them have just arbitrary terminal rays. Now here I've drawn the angle A to be in the second quadrant and the angle B to be in the first quadrant. That's not really special for these two angles. These could have both been in the second quadrant or both in the first or in the first and third or anything like that. So it doesn't matter where these angles are. All that matters is the angle A and the angle B are both in standard position. And here I want the angle A to be larger than the angle B. Beyond that, nothing else really matters. Okay, so these are two separate angles. Now, I've gone ahead and placed them inside the unit circle. And by placing them inside the unit circle, I can tell that this point will give me the sine and the cosine of the angle A. So, one definition of the sine and cosine of an angle is, if it's in standard position, the point where it crosses the unit circle, that'll give you the cosine of the angle and the sine of the angle. All right, well, that's going to be the cosine of, and again, that's the angle A, comma, that's my x-coordinate, that gives me the cosine of the angle. The y-coordinate will give me the sine of the angle. So here that's going to be sine of the angle A. All right, the x-coordinate, the first coordinate, that's the cosine of the angle. The second coordinate is the sine of the angle. So I'm going to label them exactly that way. Instead of x and y, I'll say cosine of A and sine of A. Likewise, over here, this point is going to be, for B, the cosine of B, the sine of B at this point here. Cosine of B, sine of B, just like that. Now, this point is common to both of them, and that's the point given by 1, 0. Because after all, it's on the x-axis, and it has a distance of 1 away from the origin, because it's on the unit circle. All right, now, I'm going to draw a third angle. You say, okay, so you have an A and a B, so you're going to draw a C next? Well, no, because even though these two angles are unrelated to each other, they're just two random angles, the third angle is going to be a combination of the two. The way I'm going to do it is I'm going to make the third angle the difference between these two. Meaning, if the angle A was 150 degrees and the angle B was 50 degrees, then the third angle that I'm about to make will be 100 degrees. 150 minus 50. Or if this one was 200 degrees and this one was 1 degree, well, then the one I'm about to make is 199 degrees. It's going to be angle A minus angle B. Okay. Now, again, it's going to be in standard position because all of our angles are going to be in standard position for this illustration. So again, I have a third angle. This one I'll draw it in blue. And again, the initial ray is over here, just like all the other ones. But now, where's my terminal ray going to be? Well, let's take a look here. Notice that between here and here, I can draw a line. In fact, let me even do that. Let me draw a line. And that line has a particular length. Okay, well, what length is that? That's going to be that long. Right? I'm not going to pull out a ruler, mostly because I don't have one at my desk and I don't feel like getting up. So it's, that long, from here to here. All right, well, the difference between those two angles is from here to here. So if I want to make an angle that represents the difference between those two, but it's going to be in standard position, so it's going to cross at 1, 0 on the unit circle, well, then this distance should be the same. So from here out to here, I have the same distance that I had before. So that'll tell me where my new angle should be. just like that. Essentially, this distance from here to here, from the orange dot to the blue, to the orange dot to the green dot, that's the same distance as from this blue dot down to this black dot here. Right? Okay, well, sure. If the difference between these is 199 degrees, then the amount that this opens should be the same as the amount that this opens, because this minus this gave me that. All right, so this angle in blue represents the angle A minus B. A minus B. And again, if that was 100 degrees and that was 1 degree, this would be 100 minus 1. That would be 99 degrees, or whatever. Huh? Okay, so now, note that, again, these distances are the same. The distance from this point in orange to this point in green are going to be the same as the distance from this point in blue down here to this point in black, 1, 0. Okay, so let me actually state that. Note that the distance from cosine A, comma sine A, remember those are just numbers, to cosine B sine B is equal to, is the same as the distance from, well, remember, that's the angle A minus B. So this is the point cosine of that angle, cosine of A minus B, comma, the sine of that angle, the sine of A minus B. Just like that. So the distance from this to this is going to be the same as the distance from the cosine of A minus B, comma, sine of A minus B, to this point in black, 1, 0. Okay, so just from a visual standpoint, yeah, okay, I guess, right? That distance is the same as that distance. And I can even write that out in words. But so what? Well, I can write this in a much more methodic way. After all, the distance between 2 points is something I could find all the way back in algebra. We use the distance formula. Here, the distance between 2 points is given by the square root of the sum of the squares of the differences between the corresponding coordinates. Or in other words, cosine A minus cosine B. And sine A minus sine B. So the distance between these two is going to be the square root of cosine A minus cosine B squared plus sine A minus sine B squared. And that's going to be the same as, it's going to equal to the distance between these two, which again, using the distance formula, is going to be the square root of this minus 1 squared, cosine of A minus B minus 1 squared, plus this one minus this one squared. Okay, well, subtracting 0 doesn't do anything, so I really don't have to write it. I can just write sine of A minus sine of B squared. If you want to write sine of A minus B minus 0, that's okay, but subtracting 0 won't actually do anything, so no big deal. So here, this equation says the same thing as this picture says. The distance between here and here is the same as the distance between here and here. Okay, so now what? Well, now I notice that both sides have squares. Both sides have square roots, which I can get rid of by squaring both sides. And that makes things a little bit better because square roots make things more complicated. So here, this is the same as saying cosine of A minus cosine of B squared plus sine of A minus sine of B squared. And there's no more square roots there. This was a distance, which means it was positive, so we don't have to worry about the square messing up any signs. Over here, we can say the same thing. That's cosine of A minus B minus 1 squared plus sine of A minus B quantity squared. Okay. Now, I can actually square this. Cosine of A minus cosine of B squared. That means cosine of A minus cosine of B times itself. Likewise here, I can square that thing. So I have a plus. That's going to be sine of A minus sine of B times itself again. And that's going to equal to, okay, so square this is there, square this is there, is equal to, well, I could square this, and that means multiplying it times itself. Cosine of A minus B minus 1 times itself. Plus, here, this one's already written out as a single term. So squaring it just squares that single term. The reason we're writing this out the long way is because these are not single terms. These are all binomials. So we need to distribute to multiply them. But this one is just sine of something squared. Okay, well then you just square that and you're done. So that one we don't need to distribute. It's a single term. When you square a single term, you just square that term. But when you square a binomial, we're going to need to distribute. Okay, so let's distribute. Cosine of A times cosine of A, that's going to be cosine squared of A. Cosine of A times negative cosine of B, that's going to be negative cosine of A cosine of B. And negative cosine of B times negative cosine of B, double negative makes that positive. Cosine of B times cosine of B is cosine squared of B. Plus, and we'll do the same thing over here. Sine of A times sine of A is sine squared of A. And sine of A times negative sine of B is negative sine of A sine of B. Again, negative sine of B times sine of A is, well, that's still a negative sine of A sine of B. And negative sine of B times another negative sine of B, double negative makes that a positive. Sine of B times sine of B, well, that's positive sine squared of B. Just like that. Is equal to, and now we can square this stuff, cosine of A minus B times cosine of A minus B. All right, well, that's going to be cosine squared of A minus B. Cosine A minus B times negative 1. All right, well, that's going to be minus cosine of A minus B. And then I do that here, negative 1 times cosine of A minus B. Well, that's another negative cosine of A minus B. And then negative 1 times negative 1, well, that's a positive 1. And then here, there's nothing to distribute. It's a single term, so I can just leave it as plus sine squared of A minus B. Okay. All right, now that looks very large and complicated. And, well, frankly, it is. But now we start to simplify. We're going to notice that a lot of things are about to start disappearing. You say, well, like what? Well, first of all, notice right here. Cosine squared of A and sine squared of A. What do you get when you take the cosine squared of A and add the sine squared of A? That's just the number 1. That's the Pythagorean identity. Whenever you take cosine squared of an angle plus sine squared of an angle, before we saw it with theta, but again, it doesn't matter what the angle is, as long as the angle is the same. Cosine squared of A plus sine squared of A is just the number 1. So here, I can replace that with just the number 1. Well, yeah, that's not the only one. Hey, look. Cosine squared of B plus sine squared of B. Okay, those angles are different from these angles, B's versus A. Well, yeah, but these are like each other. So cosine squared of B plus sine squared of B, that's also equal to 1. Here, let me color code. Let's make that one in red. So that's going to be 1. That one's also going to be 1. What else? Well, here, let's still stick with this side here. And here I have some terms that I can combine. Oh, my apologies. Right here, cosine of A times cosine of A is cosine squared of A. Cosine of A times negative cosine of B is negative cosine A cosine B. I said this one and I never actually wrote it. Negative cosine B times cosine A, let me go ahead and write it right here, is minus cosine A cosine B. There was one already, but I forgot to write the other one. So here, there's some like terms we can combine. Minus cosine A cosine B minus another cosine A cosine B, that's going to give me minus 2 cosine A cosine B. And likewise over here, minus sine A sine B minus another sine A sine B is minus double sine A sine B. Minus 1 minus another one is minus 2 of those. So now these have combined to give me the number 1 in red. These in green have combined to give me the number 1 right here in green. These two combine to give me this, and these two combine to give me this. So things are a lot smaller now. And now I still have the other side of my equation, so I can write equals. We'll notice right here, cosine squared of A minus B plus sine squared of A minus B. These are the same angle. Cosine squared of an angle plus sine squared of an angle, that's the Pythagorean identity. That's equal to the number 1. Here I have another plus 1 that just happens to be a constant. All right? So here I'm just going to copy down that plus 1 right here. Copy down that plus 1. And now these like terms combine. I have minus cosine of A minus B minus another cosine of A minus B. Well, minus 1 minus another one is minus 2 cosine of A minus B. Just like that. Let's see here. Notice I can subtract 2 from both sides. You say, why would I want to do that? Because here, these are constants. 1 plus 1 is 2. Same thing over here, 1 plus 1 is 2. So if I subtract 2 from here, again, whatever I do to one side of an equation, I should do on the other side. Here, 2 minus 2 goes away. And same thing over here, 2 minus 2 goes away. So what I'm left with is negative 2 cosine of A cosine of B minus 2 sine of A sine of B is equal to negative 2 cosine of A minus B. And finally, notice that I have the number negative 2 as a factor of each of these terms across both sides. So let me go through and divide both sides by negative 2. I'll divide this by negative 2, and I'll divide this by negative 2. And by doing that, that just gives me cosine of A minus B is equal to, this divides this to give me cosine of A cosine of B. And if I divide these, that's positive 1, so plus sine of A sine of B. And this is what's called the difference identity for cosine. What this tells us is that if I take two angles and subtract them, their cosine is not just going to be the difference in the cosines of the angles. Rather, it's going to be the cosine of the first angle times the cosine of the second angle plus the sine of the first angle times the sine of the second angle. This is called the the difference identity, because there's a minus there. This is the difference identity for the cosine function. All right, so let's take a look at that. Let's go ahead and copy that down over here. I'm just going to rewrite my result, what I got at the end of that development. The cosine of A minus B is equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. All right, and again, this is called the difference identity for cosine. We'll have a difference identity for sine as well, and we'll have a sum identity for both sine and cosine, where this will become a plus instead of a minus. All right, so let's consider an example here. Let's say I want to find the cosine of 15 degrees. You say, okay, well, let's just go to our unit circle. Yeah, the problem is 15 degrees doesn't appear on the unit circle. There's 30, 45, 60, 90, 120. There's lots of angles on the unit circle, but 15 isn't one of them. Well, it doesn't need to be, because even though 15 degrees is not an angle on the unit circle, it is an angle that we can get by either adding or subtracting two other angles that are on the unit circle. This is why we never really bothered going through and adding thousands of points on the unit circle, because just having those few that we already have, we can put those together in a way to give us lots of other angles. So here, cosine of 15 degrees, you can think of that as the cosine of 45 degrees minus 30 degrees. All right, 45 minus 30, that's 15. Okay, so that's the difference between two angles, 45 minus 30. What the difference identity tells us is that we can find that by taking the cosine of the first angle, which is 45 degrees, times the cosine of the second angle, which is the cosine of 30 degrees. Plus, now we take the sine of the first angle, so sine of 45 degrees, and then we're going to multiply that by the sine of the second angle, which is 30 degrees. Notice I'm not worried about that minus in there. All the minus tells me is that this is the right formula to use. Here I'm using the positive versions of the angle, 45, 30, 45, 30. Okay? So now I can evaluate each of those, because even though I don't know the cosine of 15 degrees, I do know the cosine of all and sine of all of these numbers. The cosine of 45 degrees, that's the square root of 2 divided by 2. That's something I know off the unit circle. The cosine of 30 degrees, that's going to be the square root of 3 over 2. Plus, the sine of 45 degrees, well, that's also root 2 over 2. That's something you got off the unit circle. And the sine of 30 degrees, that's a half. 1/2. Oh yeah, but I now have just regular numbers. Now I can multiply and simplify. The square root of 2 times the square root of 3, that's the square root of 6. The bottom, 2 times 2 is 4. The square root of 2 times 1, well, that's going to stay the square root of 2. And again, the bottom, 2 times 2 is 4. Those are going to be added. And since they already have a common denominator, we can just add. Root 6 plus root 2. You don't add those. They're different kinds of radicals. If you had 5 root 2 plus 4 root 2, you can add those. If the radicands are the same, you can add. But here, that's as good as you can do over your common denominator. And there we go. The cosine of 15 degrees is the square root of 6 plus the square root of 2 all over 4. Note this is not an approximation. This is not a decimal. Nothing was ever rounded. This is exactly the cosine of 15 degrees without any margin of error. So here the questions in this section will read things like find the exact value. Exact value means no rounding, no decimals, exactly the correct answer without any margin of error. This works whether you're using degrees or radians. The important thing though is you do have to be consistent. Here the entire problem used degrees, so it works out just fine. Radians, it's going to work the same way, but again you have to go through and use radians. Okay, so let's go ahead and have you give it a try. And let's have you do the cosine of negative pi over 12. Okay, so give that a try. First of all, you're going to write negative pi over 12 as the difference of two angles that appear on the unit circle. Because this is in radians, we're going to want to use radians all the way through. If you start with degrees, use degrees. If you start with radians, use radians. All right, go through and see if you can find an answer. And once you are done, go ahead and unpause and we'll go through it together. All right, so let's take a look here. You can write cosine of negative pi over 12. You can write that as the cosine of pi over 4 minus pi over 3. Just like that. Here you might say, well, how did you get that? I mean, did you, what do you do to get the two numbers that you subtract to give you this so quickly? Well, remember, the numbers on the unit circle, the radian values on the unit circle, all have different denominators, but you can think of all of them as having a common denominator. Right? All the denominators that you see on the unit circle are either 3, 2, or 4. And the least common denominator of those is going to be 12. So you can say, okay, well, let me think. What are the numbers that I have on the unit circle? I have 0, I have pi over 6, I have pi over 4, pi over 3, pi over 2, like that. Let me use just these. If I need more, I can get more. All right, so think of these as being over 12. Okay, so think of that as being 0 pi over 12, which is true. Anything times 0 is still 0. If you double the top and bottom, that's 2 pi over 12. Here you can triple the top and bottom, that's 3 pi over 12. Quadruple the top and bottom, that's 4 pi over 12. And multiply top and bottom by 6, and that'll give you 6 pi over 12. Okay, so do I see any numbers here where if I subtract them, I'm going to get negative 1 pi over 12? Oh, well, right here, look. 3 pi over 12 minus 4 pi over 12. 3 minus 4 is negative 1. So 3 pi over 12 minus 4 pi over 12 is negative 1 pi over 12. Oh, that's what I wanted. So I want this one minus this one, which is really pi over 4 minus pi over 3. And there we go. If ever you're not sure which ones you're using, just think of the angles that you already know and give them all a common denominator. If this was, instead of 12, if this was 16, you might want to start writing these in terms of a denominator of 16 or 24 or whatever. Right? So whatever denominator you need, go ahead and think of these in terms of that denominator. All right, so now we can go ahead and use our difference identity. This is going to be the cosine of pi over 4 times the cosine of pi over 3. And then I have plus, now I want the sine of the first angle, in this case sine of pi over 4, times the sine of pi over 3. And again, I'm just substituting in pi over 4 and pi over 3 for A and for B. And now these are all numbers that I know. Cosine of pi over 4, that's root 2 over 2. The cosine of pi over 3, that's a half. Plus the sine of pi over 4, that's root 2 over 2. And the sine of pi over 3, that's root 3 over 2. And again, those are all numbers off the unit circle. Although by this point in the semester, you probably are already starting to get comfortable with at least a few of those. At least some of those should have been something that you could do off the top of your head without looking them up, without grabbing a calculator or anything like that. It's kind of like your times tables. Can you look it up? Sure. But it's going to take an obscene amount of time to have to look up every multiplication you ever do. It's going to take an obscene amount of time to have to type everything into a computer or a calculator. Something that you use very, very often, it's probably simpler to just remember how to do it. Okay? So here, that's going to be root 2 over 4, and that's going to be root 6 over 4. Given the common denominator, that's root 2 plus root 6 over 4. And there we go. So that's using the difference identity for cosine. Now you say, okay, well, you said there's going to be other identities, right? There's going to be a difference identity for sine, a difference and a sum identity for cosine. So you're going to go through that again, yeah? You're going to draw another circle, and you're going to draw different angles, and you're going to go through all that computation again, yeah? No, we're not going to do any of that. It turns out that this is the basis for every other trig identity that we're going to be looking at in this chapter. Basically, this one is the one we work hard for. Once we have this one, if you tweak it just a little bit, change this minus to a plus, change this plus to a minus, change this number to this number, this one formula gives us all the other ones. This one identity is used to generate every other identity that we'll see in this course. So this is the one we work hard for. All the rest, we just take this one and tweak it a bit. So let's go ahead and develop the sum formula for cosine. All right, so let's begin with the difference identity. I'm just going to rewrite that down here so I don't have to go back and forth. Cosine of a minus b is equal to the cosine of a times the cosine of b plus the sine of a times the sine of b. Okay. All right, so now what if one of these angles was a negative angle? You say, you can't do that. Well, why not? After all, angles can be negative. It just means that they go backwards in the opposite direction on the unit circle. Instead of going counterclockwise the way we usually do, you'd go clockwise. But there's nothing wrong with a negative angle. So here, let's say the angle B is a negative angle. Okay, so let's write this as the cosine of A minus, and now instead of having that as a B, I'm going to write it as a negative B. Okay, well, then the way an identity works is whatever change happens here, it's going to happen over here, just like with any equation. So my sine of A and my cosine of A, that's going to remain the same. But now, wherever I had cosine of B before, now that's going to be cosine of minus B. And sine of B will be sine of minus B. Well, yeah, but what's minus a minus? Well, that's plus. So cosine of A plus B is equal to, now remember, cosine is an even function. If you have a negative inside the argument, you can just get rid of it. Cosine of negative b is the same as the cosine of positive b. All right, that's what it means for it to be an even function. Remember that the cosine of negative b is exactly the same as the cosine of positive b. So here, instead of negative b, let me just write it as positive b. They're the same, so I'd rather use the one that looks easier. Oh, but the sine function is not even. The sine function is odd. The sine of negative b is equal to the negative sine of b. So I can get rid of that negative, but it's not really going to go away. It's just going to come outside. Okay, so that positive is now a negative. Okay, so negative sine of a sine of b. And this is the sum formula for cosine. The sum identity for cosine looks very much like the difference identity for cosine, except that minus is now a plus and that plus is now a minus. The cosine of a plus b is equal to the cosine of a times the cosine of b minus the sine of a times the sine of b. Right. So here, give this a try. You're going to do the same thing that we had up here, except now with a plus instead of a minus. So go ahead and find the exact value. Again, it's not something that can come out of a calculator. A calculator will give you a decimal approximation. Here we want the exact value. Find the exact value for the cosine of, let's do 7 pi over 12 this time. These aren't particularly complicated numbers just yet, because right now we're just working with the first identities in the chapter, but we'll see a few more advanced ones as we go through. All right, so go ahead and pause the video, give that a try, and once you get an exact value for the cosine of 7 pi over 12, unpause and we'll go through it together. All right, so we need to find two angles that either add or subtract to give me 7 pi over 12. Since I'm giving this example right after I give this identity, you can be fairly confident that it's going to be a sum. Oh yeah, but which one? Well, again, these all have denominators of 12. So which ones can I add to give me 7 pi over 12? Well, it looks like these two right here. 3 pi over 12 plus 4 pi over 12, that'll be 7 pi over 12. So what I'm doing is I'm adding these two numbers, pi over 4 and pi over 3. Okay, so that's going to give me the cosine of pi over 4 plus pi over 3. And that's going to be very similar to the one we just saw. All right, so if we have this value here, we're going to do that by taking the cosine of pi over 4 times the cosine of pi over 3 minus the sine of pi over 4 times the sine of pi over 3. And all of those are nice numbers that we know how to work with. Cosine of pi over 4, that's going to be root 2 over 2. Cosine of pi over 3, it's going to be a half. Sine of pi over 4, now here we're subtracting. Sine of pi over 4, that's going to be root 2 over 2. And the sine of pi over 3, that's root 3 over 2. So putting that together, that's going to be root 2 minus root 2 times root 3 is root 6 over 2 times 2 is 4. And that is the exact solution for the cosine of 7 pi over 12. Now, just like the sum identity for cosine was proven using the difference identity for cosine, once you have an identity, you can actually use that to build other ones. Once we have these two, we can use them to build the next set. Let's talk about the cofunction identities. All the way back in chapter 1, we mentioned that we have 6 trig functions, sine and cosine, secant and cosecant, tangent and cotangent. It seems like they're paired together. There's something about secant and cosecant that somehow they're paired together, like one is the partner of the other. Okay, so what exactly is that relationship? What makes one co-function of the other? What makes cosine pair with sine? What makes cotangent pair with tangent? Well, here we're going to see what it is. I'm going to go ahead and prove one of the cofunction identities. In fact, I'm going to prove the one for cosine because that's the one we are most familiar with from what we've just proven. However, this will be true for all of them. So note that we have the cosine of the angle A minus B, and here I'm just rewriting the difference identity for cosine, is equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. Okay. Now, in examples that we've seen, we've substituted both of these for numbers. Oh, pi over 3 and pi over 4. Pi over 6 and pi over 2, or whatever. Well, we don't have to substitute both of them. Here, we're going to develop another identity by substituting just this value with pi over 2 radians, or if you prefer 90 degrees. All right. So here I'm going to say, okay, what if I said A was pi over 2? I'm going to leave B the way it was, though. Now you might say, well, why do you want to substitute with just one number? And also, how do you know you're substituting for pi over 2? Well, the reason I want to substitute at pi over 2 is because at pi over 2, some of these functions are going to disappear. Remember, the cosine of pi over 2 is 0. And in fact, the sine of pi over 2 is 1. So by substituting in pi over 2 for one of these numbers, it makes things just a little bit simpler because some of our terms are going to simplify down to be either 0, so they're completely gone, or 1, which means they don't change the remainder of the expression. So here, let's do that. What I've done is I've substituted A for pi over 2. All right, I said that backwards. I've substituted pi over 2 for A. So this will be cosine of pi over 2. I haven't changed B. And then here, sine of, again, I'm substituting a, that's going to be pi over 2, and then sine of b. But again, the cosine of pi over 2, that's 0. So this is just 0. Here, what's the sine of pi over 2? That's just the number 1. So what is anything times 0? Well, that's 0. So here this is going to give me 0 times the cosine of b plus 1 times the sine of b. Anything times 0 is 0, so that goes away. And sine of b times 1 stays sine of b. Hey, the cosine and the sine are the same result as long as they're shifted over by pi over 2 radians. Or, if you prefer degrees, 90 degrees. This is something that we see immediately when we look at their graphs. If you look at the graph of the sine function, it looks like this. If you look at the graph of the cosine function, it looks like this. Well, yeah, they're both waves, I guess, but they're different, aren't they? Well, remember, these keep going. So let me extend this over a little bit. Hey, look. Here's a wave. And here's a wave. And in fact, if I just ignore this part right here, hey, those are exactly the same. Well, except one shifted over a little. Oh, I wonder how much it shifted over by. It shifted over by pi over 2 radians, by 90 degrees. And you say, well, wait, you can ignore a part? Well, okay, if you don't want to ignore a part, you can just keep this part going. Either way, these are the exact same graph, just shifted over a little. That's why you have functions that are co-functions of each other, because they are, in fact, the same function after a phase shift. You'll also notice there's a negative in front of your argument. Not only does it involve a phase shift, you have a phase shift and a reflection. So basically, the two graphs will be the same as each other. If you take one, shift it over a bit, and then flip it. The cofunction identities are true for all the cofunctions. So these are easy to remember. The name tells you which ones belong together. The cosine of pi over 2 minus theta is equal to the sine of theta. Or you can do it the other way around. Sine of pi over 2 minus theta is equal to the cosine of theta. That's why they're cofunctions, sine, cosine. The same will be true for, I can say the secant of pi over 2 minus theta is equal to the cosecant of theta. Or I can go the other way around. The cosecant of pi over 2 minus theta is equal to the secant. And you can see that if you graph both of them, one is a phase shifted and reflected version of the other. And here I'm not going to go through and prove the other ones, although we can. But here it follows for the same reason. It has to do with the sum and difference formulas for secant and for sine and for tangent and so forth. And finally, let me go ahead and write this one down. If I have the tangent of pi over 2 minus theta, that's equal to the cotangent of theta. Or if I have the cotangent of pi over 2 minus theta, that's equal to the tangent of theta. And these are the so-called cofunction identities. Just like that. Note that we're not going to be using these identities computationally like we use some of the other ones that we've already seen. These are more used for verifying identities later on down the line. Whenever you have another identity, it's sometimes useful to have something like this to allow you to rewrite one function in terms of its cofunction. But for now, it's not really something we're going to worry about using computationally. Instead, let's take a look at another kind of example. We're still looking at the sum and difference formulas. We're going to say, okay, let's say we know that the cosine of an angle, and we're just going to say A and B, the cosine of an angle A is equal to negative 8 over 17. Now, we don't know what A is, but it's not going to matter. We also have that the cosine of the angle B is equal to negative 3/5. And again, we don't know what B is, but it's not really going to matter. And we have that the angles A and B are both in quadrant 3, meaning their terminal angles are in quadrant 3. Okay. From this, we're supposed to find the exact values of cosine of A plus B and the cosine of A minus B. All right. We're going to use the sum and difference formulas. Do not fall into this trap. Every semester I'll have people who say cosine of A plus B. Oh, let me take the cosine of A and let me add the cosine of B together. That's not going to work. You're adding the angles together. These are not the angles. These are the cosines of the angles, which can't just be added directly. If you could just add them directly, this wouldn't be true. If you could just subtract them directly, this wouldn't be true. All right? So the cosine of the angle A plus B, we have seen from the sum identity for cosine, is equal to the cosine of the angle A times the cosine of the angle B minus the sine of the angle A times the sine of the angle B. Okay, well, we know these numbers. Cosine of A is negative 8/17. Okay, so negative 8 over 17. Cosine of B, that's negative 3/5. Okay, very nice, just like that. Now, sine of A, oh, well, we weren't given that. Sine of B, well, we're not given that either. Okay, so it looks like we don't have all the information, but we can find it. Because after all, once you know cosine of A, the sine of A can be found by using the Pythagorean identity. Now, you might say, well, couldn't I use the cofunction identity? After all, cosine and sine. Well, that's true, but that would require you to know what the angle here was. And here we never actually did know what that was. If I knew what this angle was, well, then I knew that the cofunction would be pi over 2 minus that angle. But that would require me to know what this angle is. Same thing over here. I would have to know what this angle is, which I don't. But I don't need to know those because I have the Pythagorean identity that I can also use. I know that the cosine squared of the angle A plus the sine squared of the angle A is equal to 1. Oh, but I know cosine of A, which means I know how to square it. Negative 8 over 17, quantity squared, plus sine squared of A is equal to 1. I know how to square those. When I square a fraction, that's the same as just squaring the top separately from squaring the bottom. If I square a negative 8, that's going to be positive 64. If I square a 17, that's going to be 289. Plus sine squared of A is equal to 1. Just like that. And now I can go ahead and subtract this from both sides. If I subtract 64 over 289 minus 64 over 289 from both sides, that's going to give me sine squared of A is equal to, let's see, 1 minus 64 over 289, that's 225 over 289. And finally, I can take the square root of both sides to get my result. Now, when I take a square root, I have both a plus and a minus. But remember, the angle A is in quadrant 3. And in quadrant 3, sine and cosine are both negative. All right. So here, even though it should be plus or minus, I know that in quadrant 3, the sine of a should be less than 0. It should be negative. So here I'm going to get that the sine of a is equal to the negative square root. The square root of 225, that's going to be 15. And the square root of 289, that's 17. All right, and there we go. So now I know the sine of a, that's going to be negative 15 over 17. And I can do the same thing to find the sine of b. All right, here I'm going to have the cosine squared of b plus the sine squared of b is equal to 1. All right, well, let's see. Cosine of b is negative 3/5. So negative 3/5 squared plus sine squared of b is equal to 1. Squaring that's going to give me 9 over 25 plus sine squared of b is equal to 1. And now I can subtract this from both sides. If I take 1 minus 9 over 25, that'll give me 16 over 25. Sine squared of b is equal to 16 over 25. And now taking the square root of both sides, normally I should have a plus and a minus. But again, in quadrant 3, sine of b should be negative. So here I have the negative root. So the sine of b is going to equal to the negative square root. Square root of 16 is 4. Square root of 25 is just 5. So now I know sine of b is negative 4 over 5. Negative 4 over 5. And there we go. So now we have all of these numbers which we can now put together and simplify. Notice I have a common denominator. All right. Common denominator, 17 times 5, that's going to be 85. So let me write all that over 85. Here, negative 3 times negative 8, that's positive 24. Minus negative 15 times negative 4, that's positive 60. Just like that. And now we can simplify and get our result. Let's see, 24 minus 60, that's going to be negative 36 over 85. And that's our result. So this is the cosine of a plus b. Notice that we never found out what a was, nor did we ever find out what b was, and we definitely don't know what a plus b is, but we can still find the cosine of that angle by using the sum formula for the cosine. To find the difference, you would do the exact same thing, except this would become a minus, meaning this would become a plus. So here that would simply change that sign, and this would now become 100 and, no, not 100, that would become 84 over 85. All right, so here, nothing really changes except for that plus becomes a minus, that minus becomes a plus, meaning that minus becomes a plus, meaning that minus becomes a plus. So here the answer to this one will be 24 plus 60 over 85, or in other words, 84 over 85. So this one's 84 over 85. Let's talk about the sum and difference formulas for the sine function. Let's begin by noting that sine of a plus b, this a plus b is a single angle. Now, it's a single angle that's made by adding two other angles together, but it is a single angle. So here I'm going to go ahead and circle it just to keep things together. Okay? So here, the sine of, yes, that's the sum of two angles, but you should think of it as being just a single angle. So the sine of one angle. Well, by the cofunction identity, that's the cosine of pi over 2 minus that angle. Sine of an angle equals cosine of pi over 2 minus that angle. All right, so now what? Well, note that, again, this is a single angle, even though it's made up of the sum of two other angles. But we can think of it as two separate angles. So we can write this way. We can write this as the cosine of pi over 2 minus a minus b. We can distribute the negatives, that's minus a and minus b. So yes, this is a single angle, but it is made up of the sum of two other angles. So if we want to, we can split it. Okay, but now look, pi over 2 is an angle, A is an angle, and if I subtract those, this becomes an angle itself on its own, separate from B. So we can write this as the cosine of pi over 2 minus A, and that's an angle, minus some other angle, which we're calling B, like that. All of these mean the same thing, but note now, this is the cosine of an angle minus another angle. The cosine of an angle minus another angle. I can use the difference formula. All right, so let's do that. That's going to be the cosine of the first angle. Well, the first angle is pi over 2 minus A. Just like that. Times the cosine of the second angle, which is just cosine of B. And now, we're going to, again, we're using the difference formula for cosine. We're going to add the sine of the first angle, so the sine of pi over 2 minus A, times the sine of B. Okay, so that's your first angle minus your second angle. Okay, so by the difference formula for cosine, I have cosine of the first angle times the cosine of the second angle plus the sine of the first angle times the sine of the second angle. Well, yeah, but that's a cofunction identity. The cosine of pi over 2 minus A is the sine of that same angle. In other words, the sine of A. So here, cosine of pi over 2 minus A, that's the cofunction identity. That's the sine of just A. Here, I'm going to leave cosine of B alone. Plus, here, sine of pi over 2 minus A. Well, again, that's a cofunction identity. Pi over 2 minus A, well, that's going to be just A plugged into the cofunction. Oh, so if that's sine, the cofunction must be the cosine. So this will be the cosine of cosine of A, the cofunction identity, and then here's sine of B. I'm just going to go ahead and leave that alone. And that gives us a sum formula for the sine function. Here, we can write that. In fact, let's write it up here with this one. We have the sine of A plus B is equal to the sine of A times the cosine of B plus the cosine of A times the sine of B. And there you go. That's the sum formula for the sine function. We can find now the difference formula because we can say, well, look, sine of A plus B. Okay, well, instead of plus B, let's say that's plus a negative B. Instead of having an angle there, let's have a negative angle there. Okay, well, that'll replace that B and that B with a negative B. The A stay the same. So that's sine of A cosine of B plus cosine of A sine of B. Oh yeah, but the B's are being replaced by negatives. Okay, so that's negative B right there. Well, the cosine is an even function. So the cosine of negative B is just the same as the cosine of positive B. So with or without the negative, it's still the same. So let me have it without the negative. Well, yeah, but the sine function is not even. It's odd. So sine of negative B is the same as saying negative sine of B. Let's take that negative out. So that becomes a negative. The cosine of A stays the same. And now that's, since I took the negative out, that is now sine of positive B. And this is now the sine of A plus a negative B, or more simply sine of A minus B. So that's going to be the difference formula for sine. The sine of A minus B a plus a negative b, that's just a minus b. That's going to equal to the sine of a times the cosine of b minus the cosine of a times the sine of b. And notice that again, these two are very similar to each other. The difference is the positive versus the negative. Once we know a sum formula for sine and a sum formula for cosine, well, we can develop one for tangent, because after all, tangent is just sine over cosine. So here, let's go ahead and develop one for tangent. Let's see if we can find the tangent of a plus b. Well, by definition, or by using the quotient identity, the tangent of a plus b is the sine of a plus b over the cosine of a plus b. Well, yeah, but I know what both of those are. I have them up here. They are my sum formulas. The sine of a plus b is equal to the sine of a times the cosine of b plus the cosine of a times the sine of b. Sine of a cosine b plus cosine a sine of b. My denominator, that's going to be the cosine of a plus b. That's the cosine of a times the cosine of b, right, minus the sine of a times the sine of b. Just like that as a fraction. Now, we could just use that, I suppose. That could be our sum and difference formula for tangent, but that's usually not the way it's written. Usually what we want to do is we're going to simplify this out a bit. Okay, so how do we simplify? Well, there's a few ways, but the most common way is to do the following. I'm going to multiply the top and the bottom by something. Okay, what are we multiplying by? We're going to multiply the top and the bottom by 1 over cosine A cosine B. Now that might look like a strange choice, but note that cosine A and cosine B are, at least one of those exists in each of these terms. That's got a cosine A, that's got a cosine A, that's got a cosine B, and that's got a cosine B. All right? So that may seem like an odd choice, but it actually will simplify things out nicely because it's these two factors are factors in each one of our terms. Now, you can actually find other factors that are in each of our terms. So like I said, this is not the only way to simplify, but it is the most common way. All right, so let's go ahead and rewrite that as, here, I'm going to write this by dividing each of these by cosine A, cosine B. So that's going to be sine of A cosine of B over that denominator, cosine A cosine B. And you'll notice those divide, but we'll get to that in a moment, plus cosine A sine B divided by cosine A cosine B. And again, you notice some stuff's about to divide away. And now over, and I will do that here as well, cosine A cosine B over cosine A cosine B minus sine A sine B over cosine A cosine B. And now you notice a bunch of things divide away. Cosine of B over cosine of B, that's just 1. Cosine of A over cosine of A, that's just 1. Cosine of A over cosine of A and cosine of B over cosine of B, all of those just become the number 1. Okay, so what's left? Well, right here we have sine of A over cosine of A. Well, we can leave it like that, but the quotient identity lets me simplify that. Sine of A over cosine of A, that's tangent of A. So let me just write it as tangent of A. I could say tangent of A times 1, but of course multiplying by 1 doesn't change anything. So it's probably okay for us to just leave it as tangent of A. If you want to write tangent of A times 1, you can. Plus, here that's 1 times sine of B over cosine of B. Oh, that's, by the quotient identity, that's a tangent of B. And again, you can say 1 times tangent of B, but most people don't bother with the 1. Here, that's 1. And here we actually should write it, because if we don't write it, there's nothing left, right? Here, something divided into itself is the number 1. So we write that as 1. Minus, all right, sine of A over cosine of A. That's tangent of A. Well, sine of B over cosine of B, that's tangent of B. So we can write that as 1 minus tangent A times tangent B. And this is our sum formula for the tangent function. And if we want to find the difference formula, we can simply pull the same trick that we did up here. Once we have a sum formula, you can substitute the b for a minus b, and let's see what happens. The tangent of A plus B is, after all we found was that tangent of A plus tangent of B over 1 plus tangent of A tangent of B. I've just rewritten this identity. Oh, no, I haven't, because I messed up my sign here, haven't I? That should be a minus. Getting ahead of myself. That should be a minus still. But now I'm trying to take this B and change it into a minus B. Okay, so let's write that as A plus negative B. And if that's a negative B, well then these are being replaced by negative B as well. Now remember, tangent is an odd function. Having a negative inside is the same as having a negative outside. So here we can write this as tangent of A minus, and now since the minus is on the outside, we don't have it on the inside anymore, tangent of B over 1 minus the tangent of A. But again, this minus in the argument can be brought out. So this minus, along with that minus, will become a plus. And now since that minus is gone, that is now tangent of an A times the tangent of B. No more negative. So here, all that happens is that positive will turn to a negative, that negative will turn to a positive. So this gives us the sum and difference formulas for tangents as well. Here we get that the tangent of A plus B is equal to tangent of A plus tangent of B over 1 minus tangent of A times tangent of B. And if you replace that plus with a minus, tangent of A minus tangent of B, then that plus gets replaced by a minus, and that minus gets replaced by a plus. So tangent of A minus tangent of B over 1 minus tangent of A, oh, that should be a plus now, plus tangent of A tangent of B. So that plus becomes a minus, that minus becomes a plus. And there we go. We have all the sum and difference formulas for sine, cosine, and tangent. You might ask, well, what about secant, cosecant, and cotangent? Well, those are just the reciprocals of these. So if you needed to find the cotangent of A plus B, just find the tangent of A plus B, and then take the reciprocal. You want to find the secant of A plus B? We'll find the cosine of A plus B, and then take its reciprocal. So the other three are simply the reciprocals of the ones that we have now. So, as one example, let's go ahead and look at just a numerical example first. Let's find the exact value. Remember, that means no decimals, no approximations, no rounding. That should have fractions and square roots. An exact answer, no approximation. We're going to find the exact value of the tangent of 75 degrees. Now remember, 75 degrees is not something that appears on the unit circle. It's not something we know the sine or cosine or tangent of, but we can find it using our sum and difference formulas. First, remember that even though we don't know anything about 75 degrees, we know things about 30, 45, 60, 90 degrees. Oh, well, 75 is the sum of two of those numbers, 30 and 45. So here we can write this as the tangent of 30 degrees plus 45 degrees, like that. So that's going to be the sum formula for tangent, where your A is going to be 30 and your B is going to be 45 degrees. So let's go ahead and do that. That's going to equal to, we want, again, the tangent of A, so tangent of 30, plus the tangent of B, so that'll be the tangent of 45, and again, these are all in degrees, over 1 minus tangent of 30 times tangent of 45. So remember, that's plus and that's times. Okay, so now we have everything nicely set up. So now we can go ahead and find those values, substitute, and simplify. So the tangent of 30 degrees, that's going to be 1 over root 3. By this point, these numbers should start to come a little easier. We saw the unit circle at the beginning of our first chapter, the first few days of class. We've been using it over and over again. And by now, you should start to be able to get these numbers without looking at the unit circle and without doing any computation. These should start to come a little more naturally by now. Right? If not, you may wish to practice that just a little bit more. Tangent of 30 degrees is 1 over root 3. If you're having a little bit of a hard time with that still, remember that's sine of 30 degrees over cosine of 30 degrees, and then you can simplify. The tangent of 45 degrees, that's just the number 1. And that's going to be 1 minus 1 over root 3 times 1. Remember, up here they're added, down here they're multiplied. Okay, so now we're just simplifying here. We have several complex fractions. We have several fractions within fractions, so let's clean all that up. All right, so let's see. That's going to equal to, well, let's combine these by giving them a common denominator. I can take the number 1 and write it as just root 3 over root 3. And now these two have the same denominator. So 1 over root 3 plus root 3 over root 3 is 1 plus root 3 over root 3. Okay. Likewise here, I can give these the same denominator. I can make this one root 3 over root 3. And now that's going to be root 3 minus 1 all over root 3. Just like that. Common denominator is the square root of 3. That square root of 3 was one numerator minus 1, which is the other denominator. And now here these divide away. And we're left with 1 plus square root of 3 over square root of 3 minus 1. All right, so now we don't have any complex fractions, but now we still need to rationalize that just a little. So we can rationalize that by multiplying by its conjugate. Thinking back to algebra, whenever you have a irrational binomial, something like square root of 3 minus 1 like this, where this is irrational and it's made up of the sum or difference of two numbers, we can rationalize it by multiplying by the conjugate, or in other words, root 3 plus 1. Like that. Okay, so let's see what happens there. That's going to be root 3 times root 3, that's root 9. Well, root 9 is just the number 3. That's going to be 1 times the square root of 3. That's negative 1 times the square root of 3, so negative root 3. And negative 1 times 1, well, that's negative 1. On top, 1 over root 3, that's root 3. 1 times 1, that's 1. Root 3 times root 3, that's root 9, which is just the number 3. And these are all positive up here. And then root 3 times 1 is another root 3. So in our denominator, these two, oh, I forgot my plus sign right here. There we go. In my denominator, these two just subtract away. Root 3 minus root 3 gives me 0. And here, 3 minus 1 is just going to give me 2. In my numerator, 3 plus 1 is 4. Root 3 plus another root 3 is double root 3, 2 root 3. And then I can reduce these. 4 over 2, well, that's the number 2. And 2 over 2, that's the number 1. Oh yeah, but don't forget your root 3. So that's going to be 1 root 3. Or just root 3 if you prefer. And there we go. The exact value of the tangent of 45 degrees is 2 plus the square root of 3. So now let's have you give it a try. Let's give you some information. Let's say you have two angles in standard position. Let A and B be angles in standard position. Such that the sine of the angle A is equal to 4/5. The cosine of the angle B is negative 5/13. Right? So you're given those values, and you're also given that A is somewhere between pi over 2 and pi. Oh, well, that means that it's somewhere in quadrant number 2. The angle 0, the angle pi over 2, the angle pi, the angle 3 pi over 2. If it's between pi over 2 and pi, that means it's over here in the second quadrant. You're also told that the angle B is somewhere between the angle pi and the angle 3 pi over 2, meaning it's over here in quadrant number 3. All right. So given all that information, the question is to find the exact value of the sine of A over B, not A over B, A plus B. And the other question is, and find the quadrant of A plus B. In other words, once you add A and B together, which quadrant does it terminate in? Find the quadrant of A plus B. Okay. So go ahead and give that a try. This one you might think about for a little bit, but this one really is just using the formula that we derived just a moment ago, namely the sum formula for sine. We've already seen an example of tangent, so sine is the one we want to use here. So go ahead and pause the video, give this a try, and once you have a result, go ahead and unpause and we'll go through it together. All right, so we're given the sine of A and the cosine of B. Well, we know that to find the sine of A plus B, we're going to be using this second formula here, which requires us to know the sine of A, which we have, and the cosine of B, which we also have. But we're also going to need the cosine of A and the sine of B, which we don't have. So we need to find those first. And fortunately, since we already know sine of A, we can find cosine of A by the Pythagorean identity, and same thing for B. So let's see here. Sine of A squared plus cosine of B squared is equal to 1. Well, I know sine of A, that's 4/5. So this would be 4/5 squared plus cosine squared of B equals 1. Squaring this is going to be 16 over 25 plus cosine squared of B is equal to 1. And now let's subtract this over to the other side. You have 1 minus 16 over 25. You're going to get 9 over 25. And that's the cosine squared of B. Oh, these should all be A's, shouldn't they? Because I'm using sine of A. And the Pythagorean identity only works if you have the same angle. So yeah, these need to be the same angle. All right, so why did I put B? Oh, because I was looking at this. Here, these need to be the same. So cosine squared of A is equal to 9 over 25, which means that if I take the square root of both sides, I get that the cosine of A is plus or minus the square root of this. And the square root is going to be a 3 on top and a 5 on the bottom. Okay? But we know that the angle A is somewhere in quadrant number 2. And in quadrant number 2, what is the cosine? Is it positive or negative? Well, it's definitely negative in the second quadrant. So, but A is in quadrant 2. So we know that's got to be negative 3/5. And there we go. So now we know sine of A and cosine of A. We know cosine of B. So now we can find sine of B. So let's go ahead and do that. Sine squared of B plus cosine squared of B is equal to 1. Now remember, the Pythagorean identity works either way. Cosine squared of B plus sine squared of B, or sine squared of B plus cosine squared of B. Addition's commutative. It doesn't matter what order they're in, but it does matter that these angles be the same. A with A, B with B. All right, so I know cosine of B is that number there, negative 5/13. So let's plug that in. This is sine squared of B plus negative 5/13, and again that's being squared, is equal to 1. All right, so that's going to stay sine squared of B for now. But squaring this will give me plus negative 5 squared is 25. 13 squared is 169. And all that's going to equal to 1. So now take this and subtract over to the other side. That'll leave you your sine squared of B all by itself. Here, 1 minus 25 over 169. That's going to be 144 over 169. Just like that. Subtract this from both sides. And now we're going to take the square root. Okay? Let's see here. So taking the square root gets rid of the square. That's going to give me the sine of B is equal to plus or minus that square root. Okay, well the square root of 144 is 12. And the square root of 169 is 13. It's nice they gave us nice whole numbers. Every once in a while you get nice whole numbers, but also there's plenty of times where you end up with like a square root somewhere, as we saw in the previous problem. As we saw over here. Right? It happens one way, sometimes happens one way, sometimes it happens another way. So here we get that the sine of B can be either of those, but it shouldn't be either one. Let's see. I know that the angle B terminates in quadrant number 3. And the sine of B in quadrant number 3, well, that's going to be negative. So here, I know that B is in quadrant number 3. So that means that the sine of B must be the negative one. That's going to be negative 12 over 13. And there we have it. We have now the sine and cosine of A and the sine and cosine of B. So now we're going to use the sum formula for sine, because after all, that's what we're looking for. We're looking for the sine of A plus B, the sine of A plus B. So we're going to use this second formula here, sine of A cosine of B. Plus cosine of A sine of B. And that is going to equal to sine of A plus B. But now every one of those numbers is a number that we know. So let's just plug them all in. Let's see here. Sine of A. We know sine of A was given as 4 over 5. And the cosine of B was given as negative 5 over 13. Plus, let's see here, the cosine of A we found ourselves to be negative 3/5. and the sine of b, we found ourselves to be negative 12 over 13. Looks like that. Okay. Here we can multiply these across. That's going to be negative 20 over 85. Just like that. And I can go ahead and multiply these across. Double negative makes that a positive. Positive 36 over 85. Just like that. And now we can subtract those two. All right, that's a negative. So 36 minus 20, that'll give us 16 over our common denominator of 85. And there we go. We have our result. The sine of A plus B is equal to positive 16 over 85. Okay. Now remember, there was a follow-up question. We were told, okay, find the exact value of the sine of A plus B. Okay, we found that. And then the other question was to find the quadrant of A plus B. Okay, well, let's see. We know that the sine of A plus B is 16 over 85, which is a positive number. Okay, well, in what quadrant is the sine of an angle positive? Well, there's two of them. Sine of an angle is positive either in the first quadrant or in the second quadrant. Well, let's see. If we knew the cosine of A plus B, that would narrow it down. Because if the cosine is positive, that would be quadrant 1. If the cosine was negative, that would be quadrant 2. So we can go through and use this information that we already have to find the cosine of A plus B. Note that we don't need to find any more information. We have everything we need. We just need to reorganize it a bit. The cosine of A plus B, that's equal to, and that was one that we had from a previous section, the cosine of A times the cosine of B minus the sine of A times the sine of B. And notice those are all the numbers that we had before. We're just putting them together in a different order. Cosine of A, that's negative 3 over 5, times the cosine of B, that's negative 5 over 13. Now there's a minus there in the middle. Sine of A, that's 4/5. And sine of B, that's negative 12 over 13. All right, so double negative makes that a positive 15 over 85. Here, that's minus, but there's another minus, so that'll become plus. That's 48 over 85. And, oh, you know what? 13 times 5 is 65, isn't it? Should be 65. Same thing up here. 13, that should be 65, yeah. My apologies. I was focused on making sure the numerators were correct. I got sidetracked a little. There we go. 16 over 65. That doesn't change anything about the nature of our answer. It was just a little misstep there. All right, so let's see here. Where were we? Oh, 15 over 65. Double negative makes that a plus, so that's plus 48 over 65. And we can add those together, and that'll give us what? 48 plus 16 will give us 63 over 65. And that will give us the cosine of A plus B. Okay, so we're looking for the quadrant of A plus B. We already know the sine is positive, and we just found that the cosine is positive. So if the sine and the cosine of this angle is positive, what quadrant must that angle rest in? Oh, there's only one place where both sine and cosine are both positive, and that's in quadrant 1. So since sine of A plus B is positive, and the cosine of A plus B is also positive, then A plus B must be in quadrant 1. and that makes us happy. Okay, as our last problem of the section, let's take a look at not a numerical problem, but let's take a look at something we saw at the beginning of the chapter, and that's verifying an identity. So now we have when we saw verifying identities, we stated that basically you're going to use the basic identities that you already know to reform one expression into another. Well, now we know more than just the basic ones. Now we have the sum and difference formulas for sine, cosine, and tangent, which, yes, they may be one new type of function, one new type of identity on these functions, but even that one new type, the sum difference formulas, the sum difference identities, can still increase the amount of computation and the amount of rewriting that we can do. So here, as an example, we're going to go ahead and verify the identity. And the identity we wish to verify is that the sine of x plus y divided by the cosine of x minus y is equal to the cotangent of x plus the cotangent of y over 1 plus the cotangent of x times the cotangent of y. So, as in previous sections, whenever we verify an identity, we start by simplifying the more complicated side. Here it's sort of a matter of opinion which one's more complicated. But personally I think, well look, these arguments are all single expressions. Here I have arguments that are big. Here I have just one trig function. Here I have two. So I feel like this one's more complicated. You may have a different opinion, in which case you might start from here. But I'm going to start from here. So I'm going to take the sine of x plus y over the cosine of x minus y. And I have ways of rewriting both of these. The sine of the sum of two things, well, that's the sum formula for the sine function, which is going to give me the sine of the first part, sine of x, times the cosine of the second part, which is cosine of y, plus the cosine of the first part, cosine of x, times the sine of the second part, sine of y. All right, so that's the sum formula for sine. In previous problems, we've had a and b. Now it's x and y. Same idea. For the cosine of of x minus y, we're going to use the difference formula, but instead of a and b, we're going to say x and y. But it's still the same identity. The cosine of a minus b, the cosine of x minus y, is the cosine of the first part, cosine of x, times the cosine of the second part, which is cosine of y, plus the sine of the first part, sine of x, times the sine of the second part, sine of y. Now, if I look at my current denominator, I start to note the pattern that I want. I have something times x, and then that same something, something of x times that same something of y. Well, I have that occur twice over here. Here I have cosine x, cosine y. Here I have sine x, sine y. Yeah, but neither of those are right. I want cotangent x, cotangent y. Okay, well, can I make cotangent of x, cotangent y out of either of these? Well, yeah. Right here, if I divide this by sine of x, sine of y, that's going to give me cosine of x over cosine of x, cosine of x over sine of x. Well, that's cotangent of x. And cosine of y over sine of y, that's cotangent of y. So here I notice the pattern is similar, and I try to make it exactly the same. If I divide these by sine x, sine y, these will become this. You say, well, what about the rest of the stuff? Well, that might be enough, or maybe not. Maybe there's more stuff we need to do. But I know I need to be moving in that direction, so let me give that a try. So what I'm going to do is I'm going to multiply both the top and the bottom of this by 1 over the sine of x, sine of y. And I'll do the same thing over here. 1 over sine of x, sine of y. All right, so that's going to equal to, basically I'm just dividing every one of these things by sine x, sine y. All right, so that's going to be sine of x cosine of y, sine of x cosine of y, and that's being divided by sine x, sine y. Okay, and then plus, and now I have cosine of x, sine of y, over sine x times sine of y, all over. Now I have cosine of x, cosine of y over sine x, sine y, which is going to give me this. Okay, so at least I'll have that part. Maybe I still need to mess with the rest of it, but at least that's a good start. So I have cosine of x, cosine of y, over sine of x, sine of y, plus sine of x, sine of y over sine of x, sine of y. Okay. All right, so let's go ahead and start simplifying whatever we can. Well, let's see. Here, these divide away and these divide away. So that just leaves me 1, and that just leaves me 1, and 1 times 1 is 1. Okay, cool. So here in my denominator, I have this plus 1. Okay, over here, sine of y divides sine of y, and that gives me 1. Okay, so I have this times 1. Okay, so let me write that down. That's going to be cosine of x over sine of x. I could also write times 1, but that won't change anything, so I'll leave it alone. And then over here, these divide away. Sine of x divides sine of x to give me 1. And I'm left with cosine of y over sine of y. And here, that's cosine of x over sine of x, which is something I was after. I was trying to make that happen. And that's going to be cosine of y, sine of y, or over sine of y. All right, but now, by the quotient identities, each one of these can be simplified. In fact, they simplify to what we wanted. So here, cosine of y over sine of y, that's cotangent of y. So that's cotangent of y. Here, cosine of x over sine of x, that's cotangent of x. And there's a plus sign right there, so plus cotangent of x. And then over here I have, well, same thing. That's cotangent of x, and that's cotangent of y. So cotangent of x times cotangent of y plus 1. And now that's what I wanted. Here, addition is commutative, so I can change the order of these. Yeah, the first one plus the second one, that's the same as having the second one plus the first one. And same thing over here. The first one plus the second one is the same as having the second one plus the first one. Addition is commutative, so I can change the order of addition however I like. So I get cotangent of x plus cotangent of y over 1 plus cotangent of x times cotangent of y, which is what I was trying to confirm. So this shows that step by step we can transform sine of x plus y over cosine of x minus y to equal cotangent of x plus cotangent of y over 1 plus cotangent of x cotangent of y. And this confirms the desired identity. And that is it for our section. If anybody has any questions, comments, or problems, please make a note of those and reach out. Talk to me during our next meeting, during office hours, and let me know what you need. If anybody has any problems, let me know, and I hope you all have a nice day.